Welcome back to the Deep Dive. We're the place that takes complex research and, well, makes it directly useful for you.
That's the goal.
And today, we're diving deep into something pretty fascinating. The geography of top-tier science. Where does success actually happen?
Right. We're digging into the paths of Nobel laureates.
Exactly. If you're thinking about a career in, say, biology or maybe chemistry, physics, this is crucial. How do you reach that absolute peak?
The Nobel Prize level.
Yeah, the Nobel Prize. We're using a big analysis from Nature, looking at all the science laureates this century, basically mapping out the journey.
It's like a career shortcut, showing where the real opportunities are concentrated globally.
Okay, so let's jump right in with the headline finding. It's pretty striking. Since 2000, we've had 202 science Nobel winners in physics, chemistry, and medicine. Now get this, over 30% of them.
That's 63 people.
63 laureates won the prize while living outside the country they were born in. Think about that. Almost 1 in 3 top scientists are immigrants, career-wise. Often, they've moved more than once, too.
And you know what's really interesting is this isn't just a recent thing.
Oh, really?
No, it's a long-standing pattern in science. You look back, you see figures like Albert Einstein, right? German-born, moved to Switzerland, ended up in the U.S.
Sure, classic example.
Or Marie Curie,
Yeah.
Polish, moved to France to do her groundbreaking work. So this movement, it's not random. It looks, well, strategic.
Strategic, towards resources, you mean?
Exactly. Which raises that big question for anyone listening, especially someone planning a science career. Is moving internationally almost a requirement for reaching the very top?
It certainly looks that way from the data. And there's a great quote from economist Ina Ganguly that just nails it. She says, "Talent can be born anywhere, but opportunities are not."
That really sums it up, doesn't it?
It does. It feels like the engine behind this whole global flow of scientists.
Yeah, and it's very much a calculated thing. When you look at why these laureates moved, it wasn't just for, a change of scenery.
Right.
They were chasing very specific, very high-level scientific opportunities. We're talking the best training programs, access to specialized, often unique equipment.
And maybe the right colleagues, the community.
Absolutely. Strong research communities, the chance to work with the leading figures in their field. It's all about maximizing their scientific output.
So it's strategic career planning on a global scale.
Precisely.
Yeah.
For someone listening, thinking about their own path, it suggests you might need to prioritize the institution, the lab, the resources over, say, staying close to home.
And we see this happening right up to now. Look at the 2025 winners. The pattern holds.
Still strong.
In chemistry, Omar Yaghi, born in Jordan, now in the U.S. Richard Robson, born UK, did his prize-winning work down in Australia.
Okay.
Then in physics, Michel Devereux from France, John Clark from the UK, both ended up as U.S. residents when they got the call from Stockholm.
So it's a consistent flow, particularly towards the U.S., it seems.
Yeah, and it's not just about getting that first job out of grad school, is it? It seems like a continuous process.
Definitely. It's about being where the best science is happening at that moment in your career.
I love the quote from Andrei Geim. He won in physics in 2010, Russian-born. He said he bounced around like a pinball.
Oh, that's vivid.
Isn't it? Russia, Denmark, the UK, the Netherlands. And his reason was simple. If you stay put your whole life, you miss half the game.
That captures the mindset perfectly, I think. To really push the boundaries, especially in certain fields, you need that flexibility.
Like willingness to move.
Yeah. You follow the funding, you follow the unique equipment, you follow the cluster of expertise. The best places attract the best people, and that creates this powerful cycle.
Okay, so if opportunity drives this, let's pinpoint the main destination. Where is this talent ultimately landing?
Well, the numbers are pretty stark. The United States is far and away the biggest magnet.
How big?
Of those 63 Nobel laureates we mentioned since 2000, 41 of them were living and working in the U.S. when they won the Nobel.
41 out of 63? That's
Yeah.
huge. Is that just because the U.S. is, well, big? Or is there something specific structurally?
That's a really important question. It's not just size, it's history and structure. After World War II, and especially during the Cold War space race era.
Right, the Sputnik effect.
Exactly. The U.S. made these massive, sustained investments in science funding. Think NSF, NIH.
Okay.
That built up an unparalleled infrastructure. Top universities, national labs, big funding plots that could support really ambitious, expensive projects.
So it became a place to go.
It did. As Ina Ganguly said, it became the destination for top students and scientists globally because it just offered resources and scale that few others could match. And crucially, it still largely does.
Okay, U.S. dominates. What about number 2? Is there a clear second place?
There is, although it's quite a way behind. The United Kingdom is the next most common destination.
How many laureates landed there?
7 of the foreign-born laureates were based in the UK when they won.
7. Okay, so still significant. But wait, here's where it gets kind of contradictory, isn't it?
How so?
The UK is the second most popular destination, attracting some talent. But the data also says it's the biggest exporter of its own future Nobel winners.
Ah, yes, the UK paradox. That's a really key finding for anyone thinking about global careers.
So it attracts some, but loses more of its own top talent.
That's what the numbers show. 13 laureates who were born in the UK actually won their Nobel Prize while living elsewhere.
13 left. That's almost double the 7 foreign-born winners that they retained.
Exactly. So while the UK clearly has excellent science and trains people well initially, it seems to struggle to hold on to its very brightest stars in the long run.
Why? Why are they leaving the UK specifically?
Well, according to the analysis, it often comes down to, frankly, better offers elsewhere, primarily the U.S. Higher salaries, definitely, but also significantly larger research grants, more funding opportunities, and maybe the prestige that comes with some of the top U.S. institutions.
So competition.
Fierce competition. Caroline Wagner, a science policy expert cited in the source, points out that once researchers reach that elite level, they often follow the resources. And the biggest pools of resources are often in the U.S.
Interesting. So the UK trains them well, but then
They get recruited away, often. And it's not just the UK losing talent.
oh, who else?
Germany is next, with 6 laureates born there winning elsewhere. Japan, France, Russia. They each saw 4 of their native-born talents win Nobels abroad.
So even countries with strong science traditions are seeing a net outflow at the very highest level.
Right. It paints a picture of brain circulation that, at the Nobel level at least, heavily benefits the U.S.
Okay, let's shift gears slightly. For you listening, maybe you're focused on a specific field, like biology. Does this need to move apply equally across all sciences?
No. And this is a really important takeaway. The pressure to move varies quite a bit depending on the discipline.
How so?
There seems to be a strong link between how much expensive specialized equipment a field needs and how likely its top people are to have moved internationally.
Okay, let's see the numbers for those 63 mobile laureates. How does it break down by field?
Physics has the highest share. 37% of physics laureates since 2000 were foreign-born.
37%. Okay.
Chemistry, it's close behind at 33%.
Right.
But medicine, which includes a lot of biology-related research, has the lowest proportion, only 23%.
23% in medicine versus 37% in physics. That's a noticeable gap. Why?
This comes back to what Caroline Wagner calls the equipment hypothesis.
Okay.
Physics, especially certain subfields, is incredibly equipment-heavy. Think particle colliders, huge telescopes, specialized reactors, complex laser setups.
Things that cost billions and aren't built just anywhere.
Precisely. They exist in only a handful of places worldwide, like CERN or specific national labs in the U.S., maybe elsewhere. If your research depends on that kit, you have to go where it is.
So if you're dreaming of working on the Large Hadron Collider, you're basically planning an international career from day one.
Absolutely. Your grad school choice, your postdoc, it's all mapped around getting access to that unique infrastructure. You don't have much choice geographically if you want to play at the highest level.
Okay, makes sense for physics. How does that contrast with medicine and biology?
Well, relatively speaking, medicine and many areas of biology are seen as not an equipment-heavy field.
Hold on, medical research labs look pretty complex and expensive to me.
Oh, they absolutely are. Sophisticated labs, imaging, sequencing, animal facilities, clean rooms, it all costs a lot. But the need for truly unique, geographically fixed billion-dollar scale machines is generally lower than in, say, particle physics or cosmology.
Ah, I see. So a top-tier molecular biology lab could, in theory, be built in more places.
Exactly. It's more replicable. If a university or a country decides to invest heavily, they can build a world-class biomedical research center. It doesn't require a one-of-a-kind machine that only exists in Switzerland.
So the key insight for our listeners, especially in biology,
If your work is primarily lab-based, maybe involving molecular techniques, genetics, cell biology, things that can be done in any really well-funded institution, your chances of reaching the top without having to move internationally are statistically higher.
that offers more flexibility, potentially.
It does. It's a different kind of career calculation compared to someone needing access to a specific national synchrotron light source, for example.
That's really practical insight. Okay, so we've seen this successful flow of talent for decades, but now things might be changing.
Yes, the sources we looked at raise some serious concerns here. This vital international movement of scientists is facing uh, growing obstacles.
Obstacles that could threaten this whole system, maybe lead to brain drain from certain places or just slow down discovery.
Potentially, yes. We're seeing definite policy shifts in several key countries that are making mobility harder.
More protectionist, maybe?
It seems that way. And it complicates things, especially for younger researchers who often rely most on that international experience early on.
Okay, let's get specific. What obstacles are we talking about? Starting with the U.S., the main destination.
Well, in the U.S., there's been talk and, in some cases, action on grant cuts, reducing science funding overall. That obviously makes it less attractive.
Less money, fewer opportunities.
Right. But also, there are significant moves on the immigration front. One really stark example mentioned is a proposed new fee for the H-1B visa,
How much?
100,000 US dollars
100,000.
for a visa application.
For the application fee, yes. Now, the H-1B is the workhorse visa for foreign researchers, postdocs, skilled lab staff in U.S. universities and labs.
So who pays that? The researcher, the university.
Yeah, it's the key question. A university department trying to hire, say, a postdoc from abroad who might earn 50, 60K a year is almost certainly not going to be able to afford a $100K visa fee on top of that.
It sounds prohibitive. It could just shut down that route for many.
It really could. It risks cutting off a major pipeline of international talent into the U.S. academic system, especially at those crucial early career stages. Wow, is this kind of thing happening elsewhere too? Or just the U.S.?
No, it's not isolated. Australia, for instance, has brought in caps on the number of international student enrollments.
Limiting the intake of grad students.
Exactly. Slowing that inflow of talent at the graduate level. And Japan has apparently proposed cutting financial aid specifically for graduate students coming from other countries.
So fewer resources for international students there too.
Right. These policies, whatever the domestic reasons behind them, collectively send a signal that the welcome mat for international scientists might be getting pulled back slightly. It makes planning that strategic international move feel, well, riskier.
And the potential consequence for science itself.
Caroline Wagner's take is pretty blunt.
Yeah.
Restrictions like these will slow the rate of highly novel research, period.
Just slows everything down.
If you restrict the flow of diverse talent and ideas, you likely slow down innovation, which raises a huge question for you, the listener, planning your studies or early career right now.
If the traditional powerhouses become harder to get into, what do you do?
Where do you place your bets? If places like the U.S. and maybe the U.K. become more difficult or expensive to access, the whole strategic map has to change, doesn't it?
New opportunities might emerge elsewhere.
Inevitably. Regions or countries that are investing, that are welcoming international talent, they're likely to start picking up the researchers who can no longer easily go to the traditional hubs.
Okay, let's try and wrap this up. What are the absolute key takeaways for someone planning their science career, maybe in biology, based on this?
First, recognize that reaching the absolute top in science often involves international mobility. It's almost built into the system.
Especially in fields needing that big, expensive equipment like physics, maybe some chemistry.
Right. Second, if you're in a field like medicine or much of biology, which is less dependent on unique, fixed infrastructure.
Your path might offer more geographic flexibility. Staying home and reaching the top is statistically more plausible.
Plausible, yes. Third, the U.S. has been, and arguably still is, the dominant global hub, the main magnet.
But, and this is a big but, access is becoming more challenging due to funding pressures and, significantly, those potential immigration policy changes.
Exactly. Which leads to the final point.
Yeah.
Keep a very close eye on these policy headwinds and also on which other countries are actively investing in opening their doors.
Which brings us to that final provocative thought to leave you with.
Go on.
If talent flows to opportunity and funding, and if the established leaders like the U.S., maybe Australia, Japan, start putting up more barriers, where will that talent go next?
Which countries might become the new major science hubs over the next decade or two?
Who stands to gain from this potential shift, and what does that mean for where the next big breakthroughs will happen?
That changing map is something anyone serious about a global science career needs to be watching very, very closely right now.
Absolutely. Food for thought. That's all for this deep dive.
Thanks for tuning in.